So why did we do all this stuff with the binomial coefficients, rather dry mathematics? And the reason we did that is because it leads us to one of the most important fundamental models in all of statistics. And that is the binomial distribution. Here it is. Now, with all these models, including the model of independence that we looked at and Sally Clark got hurt with, have requirements. They have conditions under which they are. And those conditions have to be satisfied in order for the model to be properly applied. And it wasn't in the Sally Clark situation. But moving on to the binomial distribution, here are the conditions under which we can apply the binomial distribution. So what it is it is a sequence of independent, so that's condition one, independent Bernoulli trials, and that's because the early work on this stuff was done by Jacob Bernoulli, brilliant mathematician from a brilliant family of mathematicians. So these independent trials result in either 0 or 1. But we do n of them. We don't just do one of them, we do n of them. And the probability of success at every single trial, call it P. So the probability of spinning that coin, getting ahead at any trial, is constant. So either P is a half or not, but it doesn't matter. It's constant every time you do one of these trials. The probability of success remains the same. And what are we interested in? We're interested in the total number of successes. So the conditions are independence, a fixed number, n, and a constant probability. So those are the three conditions we have to be concerned with. Independent, fixed number, and constant probability of success. If we have this situation, so now these are the mathematical constraints. Now, if we're going to apply this, we're never going to satisfy the mathematical constraints or assumptions precisely, because that's mathematics. It's in the mind, all right? So we are going to be applying this. Maybe our independent trials will be independent patients, one patient after another. Okay, should we assume them independent? If we can, then, or approximately so, then we can use the binomial distribution. If we can't, then we shouldn't. Okay, is the probability of success the same at every trial? It has to be. Are we going to do this until we see the first head appear, or are we going to do this 20 times or 19 times, whatever? Okay, those are the questions we need to ask in order to apply this model. If the conditions are satisfied, then we'll be able to apply this model. So, for example, in the fourth quarter of 1988, there were 21,835 births in the Commonwealth of Massachusetts in the fourth quarter, and that were tested for HIV. Now, it's an antibody test, so they were tested for the antibodies, as one should more properly say that. And 60 of these babies tested positive. What that means is that the antibodies means that it's the mother. If the babies have the antibodies, it means the mother was infected. So the question is, how many of these babies are also infected? All right. Now, we don't know at birth we don't know, and we only have this data for what happens at birth. They were only measured at birth. Maybe we can model it. We can argue that these 60 babies who tested positive were independent of each other. Now, we need to check really, are there any twins in there, triplets, etc., because that might violate the assumption of independence. But let's suppose we can. Then what we need to know is what is the probability that one of these babies who tested positive, in fact, has the virus. And in those days, we would argue that the probability of transmission was about 25%. So we could model this to come up with an answer of how many of these babies are infected. We don't know, but we could model it to make a probability statement by taking n equals 60 of those 60 babies who tested positive and arguing that p should be approximately 25. So we can make our probability statement from this model. An idealization, but it gives us some guidance. Okay, that's how we use models in biostatistics, in epidemiology, in public health, etc. Here it is, the binomial distribution that we would use to answer the question raised in the previous slide. So there it is. It's n combination x, p to the x, 1 minus p to the n minus x. So in that situation, we would put n equals 60, and we would put p equals 0.25. And we could answer this question for any x between 0 and n. So we can tell you what the probability is that none of the babies are in fact infected, or one of the babies, or two of the babies, all the way up to 60 of the babies. We could answer that question in this particular situation. So, but we need, in order to answer that question, we need to know what we call parameters. The parameters of the model, in this case, there are two. P, the probability of success, and n, the number of trials. So n was 60, probability of success was 0.25 in this situation. Okay, so of course you're not going to do those calculations by hand yourself. You will go to Stata, and the command in Stata is, it's a function, it's called binomial p. So the binomial probability, binomial p. It needs to know n, it needs to know p. So in this case, I went and asked it, what if n equals 10 and p equals 0.5? So what if we spin a coin 10 times, probability of success is 0.5, what's the probability of having 0 heads? And the answer is, there it is, 0.000976, so it's like 0.001. So that's one chance in 1,000. So if you spin the coin 1,000 times, you will get a 0 once in 1,000. If you do it, the probability of getting just one of those 10 tosses to be a head, you would have to, the probability is 0.01, let's say, so that's like 1 in 100. So if you spin the coin 1,000 times, you should get about 10 heads, and so on. And so there are the probabilities. So what this says that if you run the quincunx with the probability of 0.5 and n of 10, so you have 10 rows in your quincunx, then at the bottom you're going to have 11 bins, and the probability of being in a particular bin is given to you by this column here. So what do we see? Well, the first thing we notice is that we've got symmetry. So the probability of 0 heads is the same as the probability of 10 heads. Right? And that sort of makes sense because what we call heads, what we call tails, doesn't matter because the probability is 0.5. So that makes sense. If you do the 1 versus the 9, it's the same. Do the 2 versus the 8 is the same. You got perfect symmetry here, and there it is in the middle is 5, and that's the most popular one. So 5 is the most popular. And how do we get 5 actually? Well, if I say to you, look, every time I spin a coin, the chances are 50-50 of getting a head or a tail. How many in the long run should I get? And the answer you would come up with, presumably, is what Kerridge showed, about 5. So you expect 5 out of the 10. So you expect half the time you will get heads. And that's what this shows, is that the most popular value is 5. But it also turns out to be the mean. It's the expected value is also 5. Let's plot it, and this is what we get. So this is what your bin, or the histogram underneath your bin in the quincunx, should look like if you run the quincunx with n equals 10 and p equals 0.5. Go ahead and do it and see whether you get this picture or not, or how long it takes you to get approximately, even approximately, this picture. That gives you an idea of what we mean by for n large enough, when we had the definition of probability, for n large enough. Okay? Once things start getting a little bit more complex and you can take on 11 different values, then you can get an idea of how long you have to wait until you reach this long-run equilibrium situation. If we changed the p from 0.5 to 0.2, what would we expect to see? Well, this sort of tells us that the probability of a 1 is now down to 0.2. So we are much more likely to see low numbers than high numbers. They're no longer symmetric because now it's not 0.5, 0.5. Now it's 0.2, 0.8. And indeed, if we look at it, the probability of getting 0 successes is 0.107. Probability of 1 success is 0.268, and so on, whereas the probability of getting 10 successes is essentially 0. Probability of getting 9 successes is essentially 0. Even 8 successes is 0.00007. So that's like 0.301. That's like 1 in, what is that, 10,000? The most popular value now is 2. Intuitively, that's what you'd expect, because 10 times 0.2 is equal to 2, which is what you expect, because it's the expected value. It's the mean. But it also turns out to be the modal value, in this case, the most popular one. There it is. So there's 2. But we also notice that there's a right tail here, and it's no longer symmetric. If we switch the probability of success from 0.2 to 0.8, then what are we going to see? We see the mirror image. In fact, if you compare these numbers, so this is 10.8. If you compare this to the previous slide, you see that we've got the mirror image going down. It looks very much like when we went up in the previous slide. And in fact, there's the picture. So we now have the tail coming on this side. All right? And that sort of makes sense. 10 times 10 times 0.8 is 8. So that's the mean. And in this case, it also turns out to be the most popular value. Now, how can we use this model? And this is the obvious way to use this model. It tells us what to expect. In the HIV example with the babies, it tells us how to plan. It gives us an idea of how to plan for services we would need as those babies progress through life. And so we can prepare for that. So that's the direct application of these models. But there's also another way we can use it. We can reverse the logic a little bit and say, all right, let's take a look at this. Now, we see that down here, essentially, the probability of being down there, of getting a 0 or a 1 or a 2 or a 3, is essentially 0. We've actually got the exact numbers if we want to. There they are. So if you take the sum of these, you see that that doesn't amount to much anyway. So the probability of being down there is essentially 0. So we can argue like this. We can say, all right, now, in my village, I want the vaccination rate to be 80% or better. But I want the vaccination rate to be 80%. I go in my village and I choose 10 people at random from my village. And I find that of those 10, only, or let's just say 3. So 3 of the 10 are vaccinated. So now I ask the question, if indeed the vaccination rate is 80%, if indeed the vaccination rate is 80%, how likely is it that I go into a village, choose 10 kids at random, and find that only 3 of them are vaccinated? This model tells us that the answer to that is very, very, very close to 0. So what do? We then question the if statement. Because if, in fact, the vaccination rate was 80%, we don't expect to see this. Yes, theoretically it can happen, but look at the probability that it happens. It's extremely small. So, yes, it can happen. But if there's an alternative explanation, such as maybe this village was missed by the crew when they came around last time, or maybe it's time for the crew to revisit this village and offer vaccinations again. That is how we use these models.